Right. So linear algebra and optimization is what we are going to begin with. I think I was sort of not sure whether to have this or not, but given after hearing all of you in the introduction, such a varied background, I think it made sense to include this. Once again, before we begin, I must tell you, this module is meant as a refresher. I'm not going to teach you linear algebra. I'm not going to teach you optimization. That is something we have assumed. But if things are not clear, I'm not going to prove them here. I might try to give you an idea, and then I will assume that you can dig out the references and understand it in more details if need arises. Okay. This will ensure that roughly all of you are familiar with at least the terminology, not more. Right, so without wasting further time, let's begin. So based on the responses that I received to the Google form, it seems to me that several of you, majority of you, are sort of comfortable with linear algebra, or at least more comfortable with linear algebra than optimization. So even though the title says linear algebra and optimization, yesterday night, late, around 9 o'clock, I decided to switch the sequence. So we are going to first deal with optimization, because that is an area where quite a few of you are probably not comfortable. Linear algebra, a lot of you are comfortable, so there's not enough time left. We can skip it, or at least do a rapid review. Right. So optimization. What we are going to look at is what I call continuous optimization. Having said that, that of course also means there is discrete optimization, combinatorial optimization. While they also have applications in geometry processing, shape modeling, but major area or sub area of optimization that is surely going to be required is continuous optimization. So what do I mean by continuous optimization problem? It roughly fits this pattern. So you're given a function f, which is defined on the set of Rn. Right? I hope all of you are familiar with Rn. It's just the n tuple of real numbers, the n-dimensional space, as you would call it. And for every point in this Rn, you are given a scalar, a real number. So that is this function f. And you are asked to minimize this function f. Okay, so you are supposed to find the minimum value of f, as well as you are supposed to find at what x does this function get its minimum. Okay, and of course that's not all. The x that you can find, right, that you can explore, that also has certain restrictions. Restrictions are of three forms. So there are these functions h1 to hm that you can see on the slide. These are also functions from Rn to R. If I collect all these m functions together and I denote this collection of m functions as h, as defined over here, then this function h is nothing but a function from Rn to Rm. Okay, so for every x, h1 gives you one number. Similarly, hm gives you one number. If you collect all these m numbers, you have m numbers. Okay, and similarly, there are p functions that are denoted by g, g1 to gp. If I collect all these p functions together, I denote it by g, then you get a function g from Rn to Rp. Okay, now the x that you are supposed to find or look for must satisfy these constraints. These constraints in the sense that the x that you claim as the minima of f must have the values of h1 to hm evaluate to 0. Okay. Similarly, at that x, the value of the function g1 to gp must be non-positive, less than equal to 0. Okay, so these are called the equality constraints, and these are what are called equality constraints. Okay. Apart from these two types of restrictions that X should admit to, you can also prescribe the set or the subset omega, right? So omega is a subset which is given, subset of Rn. X must be restricted to omega. And of course, these functions f, g, and h, they usually are not any arbitrary functions. Right? Typically, the most simplest assumption that f, g, h might satisfy is that they are twice differentiable. Okay, I hope all of you understand what does twice differentiable mean. What does this C2 mean? The class of functions which are differentiable 2 times, okay, and all the second order derivatives are continuous functions. Okay, that is what this notation means. Then this function f. So set constraints, Vignesh has a question. So I would request all participants, as far as you have a technical question, please sort of broadcast that message rather than sending it to me privately, because you may have a question that several others may also have. It will help sort of clearing doubts for most of them. So Vignesh has a question: what sort of set constraints are we usually going to deal with? So completely depends on the problem. So for example, if X is, let's say, how much money you are going to put in N industries that you own, right? It makes sense to have, since it's the amount of money that you're going to put in, of course, it must be non-negative. Okay, so in that case, omega would be only the positive orthant of Rn. You cannot, of course, have negative money. Okay, so that is one example, and it would depend on what is the problem that you're trying to tackle. For example, if you're trying to find what is the best direction, the direction means unit vectors. So in that case, omega would be a unit sphere, surface of the unit sphere in that case. Okay, but those constraints in some sense can also be posed using equality or inequality constraints. But in general, you can also have additional set constraints. So I hope, Vignesh, that clarifies your doubt. Okay. So then the terminology, this function f that you're trying to minimize will typically be called a cost function or an objective function. And in some cases where you know from the domain knowledge that f surely cannot have negative values, in those cases, depending on the domain, you may also call it an energy function. Okay, so these are terminologies that you might encounter when you read literature in this area. Okay, and constraints of the form hx equal to 0, gx less than equal to 0, they are of course called functional constraints, and the set omega prescribes what are called set constraints. All right, and you may also want to know why am I so fussy about minimizing. You may also want to maximize cost functions in some cases. So the thing is, if I want to maximize the function f with respect to x, that is the same as minimizing the negative of that function. Okay, so rather than studying maximization and minimization separately, if you are given a problem to maximize f, you can turn it into a minimization problem. There's a question from Sarah. Is f convex? Not necessarily. If f is convex, there will be certain advantages that you will see soon, but in general, there's no guarantee that f will always be convex. And that is where actually a lot of challenges arise. Not saying that with F being convex there are no challenges. Still, non-convex objective functions, the optimization problem is much more complicated. Okay, right. And the set of points X that satisfy all constraints. Okay, by all constraints I mean inequality set constraints. All these points, call them as feasible points. Okay, so then the problem basically is you want to find a point, a feasible point that minimizes the value of the function. Okay. So then let's look at different types of minima that you can encounter. This is directly linked to Sarah's question about whether F must be convex or not. So we are now going to sort of abuse the notation. Okay, I'm going to denote omega as the set of all feasible points. Okay, please, I hope this does not confuse you with the previous slide. This omega includes points that satisfy all functional constraints as well as set constraints. Then point, it's denoted by x star, in this set of feasible points is said to be global minima if for all other points in the feasible set the value of the function is greater than equal to the value of the function at this. Okay, global in the sense amongst all feasible points, this is sort of the best point. Okay, that is what global minima means. It should be straightforward. You can sort of refine this definition even more. Right? You can have what is called a strict global minima, which means that all other points in the feasible set must have the value of the function strictly greater than that of the value of the function at the point x star. Right? In that case, it becomes a strict global minimum. And of course, without getting into the details, we would actually want to come up with global minimas or strict global minimas, right? Whichever the case may be. But you also have a different kind of minima. Somebody had a question or a remark?
Yes, sir. I wanted to ask that in point 2, why do we need
Just
to?
a minute. Can you please give me your name first?
Yes, Pratham, sir.
Okay. Yes. Go ahead.
Yes, sir. Actually, I wanted to know in point 2, why do we need to take out x star from the domain?
Right.
We
So
can keep it in
sure.
domain and still have the inequality.
Right. So just because mathematicians are lazy, since that I just didn't want, I wanted to copy paste this notation for all the rest of the definitions.
All right, sir.
Other definitions
Okay.
will not make sense. Okay.
Thank
That's
you.
the only reason. Okay. Okay. So I hope global minima, strict global minima, everybody has understood. Let me now clarify what is meant by a local minima. Okay, so point x star in this set of feasible points is said to be a local minima if there is a small neighborhood, right? No matter how small or how big. So again, I should have sort of, assuming I would have done linear algebra, I would have introduced norms first. But I hope all of you are familiar with this notation. If not, this basically means that the set of points x, right, whose distance from this point x star is less than this number epsilon. Okay, that is what this notation basically means. So in xy plane, if I take the origin and if epsilon is 1, then this set would refer to the unit disk without the boundary. Okay, all points which are less than a distance 1 from the origin. X star was the origin. Okay, so what I'm saying here is there is a small neighborhood, right, around this point x star, in which all other points in this small neighborhood have the value of the function greater than equal to the value of the function at x star. Does that make sense? Right. So, and what this epsilon could be is no restriction on that, apart from it should be a positive number, strictly positive. Cannot be 0. Because if it is 0, that means this set would contain only the point x star. Right? So this is what is called a local minima. Why? Because locally in that neighborhood, that point has the least function value. Okay, and hope you see that if I have a global minima is surely a local minima, right? But the converse, of course, is not true. Very simple example would be something like this. Function f, this is x. If I look at this point x star, right, it is a local minima, because if I look at other points in, let's say, this region, you can clearly see that the value of the function f is the smallest value at x star in this set of points. But of course, the global minima for this function is, let's call it x. Okay, and this global minima, of course, is surely a local minima. Okay, that's what a local minima is. Then refine this definition, you get what is called a strict local minima. Only difference is, in the previous case, all other points can have the same value as that of the value fx star. Strict local minima, that is not allowed. All other points in the neighborhood must have values of the function strictly greater. That's the difference between strict and non-strict. Okay, but apart from that, there is no other difference. Okay, and let me also introduce you to few notations, concepts, infimum and supremum. Anybody who is not familiar with infimum? If you are, then you can skip this and move ahead.
Sir, I am
Anyone?
not present.
Okay, sure. Right, so infimum of a set A, which is a subset of a set of real numbers, right, is a real number, let's call it P, such that all elements of this set A, right, so that's denoted by small a, are greater than equal to this real number P. That is the first condition, that an infimum, which is also sometimes called greatest lower bound, right? So P must be less than equal to all elements of that set A, and of course this doesn't uniquely define the infimum. There can be some other real number, let's call it Q, which is also less than equal to every element of the set A. If there is such a Q, then that Q must be less than equal to this P, which is the infimum. Does that make sense? So there is a small difference between a minima and an infimum. So what would be the minimum of, let's say, open interval 0 to 1? Anyone? I'm sure a lot of you know what is this. So quicker you answer, faster we can move ahead. What is the minimum of this open set 0, 1? Anyone?
0, sir, it's 0.
Or minimum is not 0 because this set does not include 0, right?
Sir, it does not exist, sir. It will be epsilon. For all points, you will get
What
point
would be
minimum.
epsilon?
Epsilon will be 0 positive, sir.
So there is no number called 0 positive, right?
Yes, sir. So then we cannot determine a specific
Exactly.
value.
So there is no minima for this set. Okay, but what is the infimum of this set?
Infimum is 0.
0.
0.
Exactly. Infimum is 0. So you can see that this P that we claim to be the infimum, that need not belong to this set A. comes from R. Okay, that's sort of the crucial difference between minimum and infimum. Minimum of the closed set 0 to 1, of course, is 0. And in this case, infimum will also agree with the minimum. Okay, that's sort of the difference between infimum and minimum. Notation is in of the subset. Similarly, we also have suprema, is also called the smallest upper bound. The definition is complementary to the definition of infimum. So the supremum is a number S that need not be from the set A, right? Such that all elements of the set A are less than equal to this real number S, and if there is any other element, there is any other real number which also is greater than equal to all elements of the set A, then this S must be less than equal to P. Okay, so think in words, the smallest upper bound phrase describes it very well. The smallest upper bound of that set. Whether that upper bound is in the set or not does not really matter. Okay. The notation is sup of P. Right, then let's look at convex functions. What do we mean by convex function, and more importantly, why are they required for optimization? So before we define convex functions, we need to first understand the definition of a convex set in Rn. Okay. So a subset in omega of Rn is said to be convex if for any two elements, for every pair of elements that you can pick from omega, all elements lying on the line segment joining A and B must also belong to omega. Okay, maybe I'll repeat this definition once more. Subset omega of Rn is said to be a convex set if for every pair of elements, okay, it's every, not any, for every pair of elements AB that you can pick from omega, right? Once you have 2 points in Rn, you can join these 2 points via a line segment, right? And the definition of a line segment is given by this. Vary T from 0 to 1, you get points. If T is 0, I get B. If T is 1, I get A. For all intermediate values of T, I get points between A and B. So all these points should also belong to this set omega. Only then omega is said to be convex. Examples? Anyone? Simple examples. Let's take R2. It's easier to draw. Square. So what do you mean by that, Sarah? So I'm asking an example of a convex set.
I got convex function, so
Oh, convex set. Anyone? Circle.
circle.
How many of you agree that this circle is a convex set? Maybe we should ask Omkar and Sarah both. What do you mean by circle? Is it quickly, at least I would define the circle to be this.
Sir, I mean in the circle, the set of all points inside the circle, and
Okay.
Sir, would convex set have like a family of lines?
No. So this is an example, right? I would sort of call this set as a disk rather than a circle. Makes more sense, at least to me. So include points on the circle as well as everything inside. If I take any 2 points, maybe a different color, this and this, join them by a line segment, clearly see all points on this line segment also are in the disk. This is not true only for these 2 points, it is true for any 2 points that you can pick. This and this chord joining these two will always be included in the disk. So there is an example of a set which is not convex. Something like this. Here and here, the line segment sort of passes through a point which are not in this segment, star shapes. Okay, so this would be non-convex set, this would be a convex set. Got it? Okay, so now that we have an understanding of what is a convex set, let's now define what is a convex function. Okay, so function f, which is defined on Rn, specifically on this subset omega, that is said to be a convex function. First of all, the domain on which you are observing the convexity of f is omega over here, that must be convex. Okay, that is important. Okay, this domain omega over which you are examining the convexity of f, that has to be convex. Okay. Then if it is convex, so if this is not convex, nothing else matters, the function cannot be convex. Okay, but if omega is convex, then for any 2 elements in this domain, right, what does this represent? The left hand side here. So the argument in the function is a point on the line segment joining A and B. Okay, and the value of the function at this intermediate point must be less than equal to t times the value of the function at the end point A plus 1 minus t times the value of the function at the point B. And this must be true for all pair of points AB that you can pick in omega and for all points lying on the line segment. Only in that case, the function f is said to be convex. Okay, I'll show you a few examples in the next slide, but I can draw a picture to visualize this. Let's take this function f, and let's say omega is entire real number, set of real numbers. Take 2 points, say A, let's say B. Value of f at A is this, A. Value of f at is E, right? And then what is the right hand side? TFA plus 1 minus TFB. So when T is 0, I have FB. When T is 1, I have FA. And T varies from 0 to 1. So the right hand side would just be straight line joining the points AFA and TFB. Okay, what this definition says is that the value of the function at all intermediate points joining A and B. So let's say this point. What is the value of the function? It is negative x. Let's call it x. This is my fx. Okay, fx must be smaller than the value of the height of this line segment, basically. This has to be true for all A and B that you can choose and for all intermediate points. Okay? So that is what is a convex function. If there is something called convex, probably expect something to be also called concave. So can anybody quickly define what is a concave function? Please feel free to interact, otherwise this becomes more like a politician's speech rather than a good class.
So in case of concave function, the reverse should be true, right?
Reverse in what sense?
The function value at a particular point should be greater than the
greater
value of the line segment at that point.
Right. Great. What is again? So see that if you observe carefully, mathematicians typically are lazy. We don't want to write all of this again. So another way to say the same thing is function f is concave if negative of the function is a convex function. Negative of f, you basically invert this along the, so you sort of reflect this along the x-axis so that you get something like this would be roughly minus f. Okay, so if minus f is convex, and of course in this case it is not, because see this straight line is lower than the value of the function. But just to explain what is the definition of concave, easiest way to do is define is to say that minus of f must be a convex function. All right. Then let's get ahead. So as I promised, I will give you a few examples. So Hitesh has a question. On the star set you drew was not necessarily concave. No, so there is no definition of a concave set. You only have convex sets. We do have concave functions. All right. So what I mean is when I say minus f is convex, so minus f is also defined on omega. Omegas, for minus f to be convex, omega must still be convex, right? So you are sort of using convex sets in order to define concave functions as well. Okay, just to give you a few examples. The first row, you can see this is a function on R. Basically looks like a bowl, right? Something that goes down and then goes up, it cannot come down again. That's basically the intuitive characteristic of the convex function, whether it is in R1, or whether the domain of the function is R2, doesn't really matter. So again, basically it looks like a bowl. Concave functions, on the other hand, they look like inverted bowls. Put the bowl upside down, you get concave functions. Okay, what about this function? A linear function. So let's say f of x equals 2x and f is defined from R to R. Is this convex? Is this concave, or neither of them? Just draw the function.
It would be neither, sir, because the every point in the function would be equal to the point in the line segment.
Right. So what is the definition?
Oh, okay.
Sir, it would be both because it holds equality.
Exactly. Right. So if I look at this f, take the points, value of this, the height of this line segment is the same as the height of this function, right? So equality is satisfied and therefore this function f is convex. How about minus f? Minus f would look like this. Just assume this passes the theory. I'm not very good at that. This would also satisfy the definition of convexity. Okay, and therefore f is both a convex and a concave function. Okay, so any linear function is both linear and affine. So this type of functions are both convex and concave. How about this function? I hope you can see it.
It changes from convexity to concavity in different regions, sir.
Right. So if I look at the function overall, the entire real number line, then does it satisfy convexity everywhere?
No.
No. So it is not convex. How about concave?
No, it would not satisfy that either.
Exactly. So this is neither convex nor concave. Okay, so you have a full variety of categories. Convex functions, concave functions, functions that are both convex and concave. There are functions that are neither convex nor concave.